Hello, AP Chemers. Hope you're having a great day. We stopped right here, the difference between combined and ideal gas law. So we said that the ideal gas law is PV equals nRT. Do-da. So that you use when you have one set of conditions, so one pressure, one volume, one amount, and one temperature. So basically, if you have three of these four variables and you're solving for the fourth. You use the combined gas law, which is P1V1 over N1T1 equals P2V2 over N2T2. That's when you have changing conditions. So if your pressure changes, or if your volume changes, or amount changes, or temperature changes. And then we also talked about the values for R. So these are the three values for R that we're going to be using. And we went over problem number 1 in class. And so we decided for this one that we're going to use the combined gas law because you have changing conditions. Your pressure changes from 55 millimeters of mercury to something else that you're trying to solve for. Your volume also changes from 125 milliliters to 650 milliliters. And so we set up the combined gas law. We crossed out the amount and the temperature because they don't mention them here, but it is understood that they are constant, so if they're the same number on both sides of the equation, you can cancel those out, which basically gives you Boyle's law at the end. So you just solve it, and then they wanted the answer in ATMs and kilopascals as well. So let's look at number 2. Suppose you have a sample of carbon dioxide in a gas-tight syringe. The gas volume is 25 milliliters at room temperature. And they give you what room temperature is, 20 Celsius. What is the final volume of the gas if you hold the syringe in your hand to raise its temperature to 37.0 Celsius? So let's think about this. Do we have changing conditions, or do we have one set of conditions? Looks like we have changing conditions because the volume changes. This is our initial volume. They want you to find the final volume. Also, we have an initial temperature and then a final temperature. So that means we're going to use the combined gas law. So P1V1 over N1T1 equals P2V2 over N2T2. They don't mention anything about pressure. So we're going to say that that's constant. So those can cross out since it's the same number. Our volume. Our initial volume is 25.0 milliliters. Our final volume is what we're trying to solve for. Over. The amount is not mentioned, so we're talking about the same sample, so the amount is the same, so we can cross that out. And then initial temperature is 20 Celsius, but remember you have to use Kelvin. So that would be 293 Kelvin. And then final temperature is 37 Celsius, which would be 310 Kelvin. So I would recommend as soon as you see a temperature, go ahead and change that to Kelvin for this chapter because we're always going to be using Kelvin. So then we can solve for V2. V2 is going to be equal to 26.5 milliliters. This is the combined gas law, but basically we solved it when we crossed out pressure and amount. That would be Charles' law. So you could have used just Charles' law, or we could use the combined gas law and cross out whatever we have that's constant. Let's look at number 3. So ammonia can be made directly from the elements according to the equation. You add nitrogen with hydrogen to get ammonia. If one begins with 12.6 liters of hydrogen gas at a given temperature and pressure, what volume of nitrogen gas is required to complete the reaction under the same conditions of temperature and pressure? So here we have basically changing conditions. You're changing the amount and also the volume, so we can use the combined gas law. So we'll write P1V1 over N1T1 is equal to P2V2 over N2T2. We'll start with pressure. They don't tell us what the pressure is. They tell us it's a given pressure and temperature, and the conditions of pressure and temperature don't change. So basically your pressure is constant, your temperature is also constant. So we can cross those out, and when we cross that out, that gives us basically Avogadro's law. Let's plug in our values. So we have for our initial volume 12.6 liters. That's for hydrogen, and that's 3 moles of hydrogen. Our final volume is what we're looking for, the volume for nitrogen, and we have 1 mole of N2. Now, how come I can relate these two? Basically, Avogadro's law also says that if you have a certain number of particles or a certain number of moles of any gas, doesn't matter what gas it is, it's going to occupy the same volume at the same temperature and pressure. For example, if you have 1 mole of any gas, whether it's nitrogen or hydrogen or something else, it's going to be 22.4 liters at STP. So we can actually compare between the two gases this way. So if you solve for V2, which is basically the volume for nitrogen, that gives you 4.20 liters. Number 4 is asking for what is the theoretical yield of ammonia in liters. So the theoretical yield will be the yield if everything goes to completion in the reaction and it goes perfectly. So the theoretical yield will be, we can do 12.6 liters of H2 over 3 moles of H2. That's going to be V2 for ammonia for every 2 moles of ammonia. And again, we're getting the moles from the equation as written here. So the volume for NH3 is equal to 8.40 liters of ammonia. So basically 3 and 4, we're asking for pretty much the same thing. They're just worded differently. Here it said, what is the theoretical yield of ammonia in liters for the reaction as written? For the reaction as written, we have the moles for ammonia compared to the moles for hydrogen. Here, it just asked about the volume of nitrogen, which is basically the same thing, and you're using the molar ratio again. Number 5 says the helium in a 1.50 liter flask exerts a pressure of 425 millimeters of mercury at 53 Celsius. Remember that whenever you see Celsius, even before you continue reading, you want to change it to Kelvin. So let's go ahead and do that. 53 Celsius, you add 273 to that, that's 326 Kelvin. So how many grams of helium are there in the flask? So again, we're going to ask ourselves, are there changing conditions? Are any of the variables changing, or do we have one set of conditions? So let's look at it. This is volume. This pressure is the 425 millimeters of mercury. This is temperature. Looks like we have one set of conditions, and so in this case, we're going to use PV equals nRT. Doo-da, doo-da. Alright, so let's plug in our numbers. Pressure is 425 millimeters of mercury. Volume is 1.50 liters. And they don't give us amount. They're asking for grams, so basically they're asking for amount. They want you to find the moles, which is N. That's what we're solving for, and then we're going to change that to grams to solve the question. So N is our variable that we're solving for. R is the ideal gas constant. Remember, we have 3 values for that we know. In this case, we want to use the 62.4 millimeters of mercury times liters over mole Kelvin. And we want to use that because our pressure is in millimeters of mercury. So we want our millimeters of mercury to cancel as well. Also, be careful when you're using PV equals nRT. You have to make sure that your volume is in liters so that it cancels with the units in R as well. Amount and temperature are always, no matter what, in moles and in Kelvin. So that's our R. And then temperature is 326 Kelvin. We're going to solve for N. So N is 0.03134 moles. And in this case, this is for helium. The question asks you for grams, so we're just going to convert the moles to grams. So put moles of helium on the bottom so it cancels, grams of helium on top. To compare between moles and grams, I use the molar mass, so 1 mole of helium is 4.00 grams. And so that is equal to 0.125 grams of helium. Let's look at number 6. It says 14.5 grams of powdered zinc were added to 150 milliliters of 1.0 molar HCl. We want to calculate the volume of gas produced under STP conditions. So this problem is a little different because we're talking about a reaction. Zinc is reacting with HCl. So remember, whenever you have a chemical reaction, first thing you do is write out your equation. So let's do that. We have zinc, so Zn reacting with hydrochloric acid, HCl, to produce. Now they don't tell us what the products are. They tell us one of them is a gas, but that's okay. We know that this is single replacement. So the zinc will come in, kick out the hydrogen, we'll get hydrogen gas, H2, and then zinc chloride. Remember, zinc chloride, you have to write a balanced or a neutral compound. So zinc is +2, chlorine is -1, so ZnCl2. And just so we can all sleep at night, we need to balance it. So there's 2 HCl. Let's write down what we have. We have 14.5 grams of zinc. We have 150 milliliters. I'm going to go ahead and convert that to liters. You don't have to do that right now. You could do it later, but I'm going to go ahead and do that. And then I also know that I have 1.0 molar HCl. So I'm going to write 1.0. You can write molar or you can write moles per liter. Same thing. We are trying to find the volume of gas produced. So the gas that's our product here is H2. So we're trying to find the volume. And we know that it's STP. So we know that that's, you can write STP or you can write, 1 atm and 273 Kelvin. Alright, so typically if we're trying to find a product, we start with our reactant, solve for moles, and then go to moles of the substance we're interested in, and then answer the question. Problem is, we're given information about both of the reactants. So guess what type of problem this is? Yep, it's a limiting reactant problem. So we need to find what our limiting reactant is first and use that. There's many ways you can do that. I usually prefer to start with one of my reactants, solve for the other. You can also start with both, solve for the product, see which one gives you the lower amount. So whichever way you prefer. I'm going to start with my HCl, solve for how much zinc I need, and see if I have enough or not. So I will start with my 0.150 liters of HCl. I'm going to convert that to moles. So on the bottom I want liters of HCl, on top I want moles of HCl, and I can link between moles and liters of a solution using the molarity. I know it's 1.0 moles per liter. Now you could have also just said molarity is equal to moles over liters. You're given the molarity, you're given the volume, so you can solve for the moles, whichever way you prefer. So that gets us to moles of HCl. Next, I'm going to go from moles of HCl to moles of my other reactant, which is the zinc. And I link between those two using the molar ratio from the equation. So there's 1 mole of zinc for every 2 moles of HCl. So my moles of HCl cancel. Now I have moles of zinc. And I'm given grams of zinc, so I'm going to go to grams of zinc here so I can compare the two numbers. So 1 mole of zinc, molar mass of zinc is 65.4 grams of zinc. Moles cancel. And if you multiply that out, you get 4.91 grams of zinc needed. So remember, whatever you calculate is how much is needed to react with your other reactant. So if I use 0.150 liters of HCl, I need 4.91 grams of zinc to react with it completely. So then you compare what you need with what you actually have. You need 4.91 grams, you have 14.5 grams. So you have plenty. You have more than enough. So that means zinc is in excess. You have plenty of zinc. HCl would then be your limiting reactant. So this is my limiting reactant. So if I want to find the product, I want to find something about hydrogen, I would use my limiting reactant, which is the HCl. Let's do that. So I'm going to start with my HCl, 0.150 liters of HCl, convert that to moles. So basically the same step as the one above it. 1 liter of HCl, 1.0 moles of HCl, because it's 1.0 molar. That gets me moles of HCl. Next, I'm going to find moles of hydrogen, so I'm going to go from moles of HCl to moles of H2. And in this case, from the molar ratio, this is a 1 to 2 ratio. That gives me moles of H2. Then I have two options. I think the easiest way, since this is at STP, you can say that 1 mole of your gas, 1 mole of hydrogen, is equal to 22.4 liters, since it's at STP. Or the other option was to stop right here, get the moles of hydrogen, and then plug it into PV equals nRT. You have the pressure and the temperature since you're at STP. You have the volume, you're solving for the volume since it's you're solving for the volume, and you have the moles because you just calculated. But I think this way is much easier. So let's do that. If you multiply that across, that gives you 1.66 liters of H2. Number 7 is next. So a 26.8 gram mixture of powdered magnesium and silver is added to an excess of sulfuric acid. 9.6 liters of gas are produced under a pressure of 1300 millimeters of mercury and a temperature of 37 Celsius. Let's convert that to Kelvin. Let's see, that would be 310 Kelvin. We want to find the percent silver in the mixture. This is an interesting question. So it's telling us we have a mixture of magnesium and silver. And together, the mixture is 26.8 grams. We're adding that to sulfuric acid, so that's H2SO4. And they're telling us that we have a gas produced, so this is a chemical reaction, we're producing a gas. And we want to find the percent of silver in the mixture. So let's first figure out what kind of reaction is happening here. If I have magnesium and silver reacting with H2SO4, this would be a single replacement. But based on the activity series, we know that silver is less reactive than hydrogen, so silver will not react. Magnesium will. So the reaction will take place between the magnesium and the sulfuric acid, and our products would be H2 gas that's going to be produced, along with magnesium sulfate. And then we're also going to get back the silver unreacted. Shouldn't have reacted, it's just the magnesium that reacted. Now they tell us that we're going to get 9.6 liters of hydrogen gas. They want the percent of silver in the mixture. Now if I wanted percent of silver in my mixture, I would need to find the grams of silver and divide that by the total grams times 100%. So I need to either find the grams of silver in my mixture or the grams of magnesium in my mixture. And if I know the grams of magnesium and the total, then I can figure out the grams of silver. So I think out of those two, probably it would be easier to find the grams of magnesium because the magnesium reacts. It produces hydrogen. We know the amount of hydrogen. So we can go from hydrogen, change that to moles, then go to moles of magnesium, and then grams of magnesium. And if I know the grams of magnesium, I can figure out the grams of silver and therefore the percent silver. I think that's a really good question. So let's start. So my first job is to go from volume of my hydrogen gas to moles of hydrogen gas. Since that's a gas, I can use the ideal gas law, PV equals nRT, to solve for that. I'm given my volume. I'm also given a pressure. Now the pressure really wouldn't apply to anything here except for the gas, so I'm going to write it under the gas here, millimeters of mercury. I'm also given a temperature, it's 310 Kelvin. So I have the pressure, I have the temperature, I have the volume, so I can solve for amount. Alright, so PV equals nRT. Pressure is 1300 millimeters of mercury. Volume is 9.6 liters. Amount of hydrogen is what I'm solving for. Now, I highly recommend whenever you have a chemical reaction like this and you're using PV equals nRT, write down next to it what substance you're doing this for. The number one mistake that people make with this type of problem is they solve for moles and then they don't know it's moles of what substance. Some people might think this is moles of magnesium or moles of silver or moles of sulfuric acid. Remember, PV equals nRT only works for gas. So it would help if you write down what substance it is for two reasons. First, when you get your answer, you know what it's for. But the other reason is that will prevent you from using PV equals nRT for something that's not a gas, for a solution or a solid or a liquid. Trust me, that happens a lot. So N is what we're solving for. R, since our pressure is in millimeters of mercury, we want to use 62.4 millimeters of mercury times liters over mole Kelvin. Temperature, we said, was 310 Kelvin. You solve for that, you end up with 0.646 moles of hydrogen. So we just found moles of hydrogen, but we were trying to find mass of one of these in my mixture. So I can go from moles of hydrogen to moles of magnesium since there was a reaction between the hydrogen and the magnesium. So I'm going to say 0.646 moles of H2. On the bottom, I'm going to write moles of H2 so it cancels. On top, moles of magnesium. And from my reaction, it's a 1-to-1 ratio. That gives me moles of magnesium that reacted. Then I can go to grams of magnesium, so moles of magnesium on the bottom, grams of magnesium on top. 1 mole is 24.3 grams. And so I end up with 15.7 grams of magnesium. Now that I know my mass of magnesium in the mixture, I know the total, I can figure out the mass of the silver. So 26.8 grams total minus 15.7 grams of magnesium is going to give me 11.18 grams of silver. And now that I have my mass of silver, I can say percent silver is equal to the mass of silver over total mass times 100%. So that's going to be equal to 11.18 grams of silver over 26.8 grams total times 100%. And if you solve for that, that's going to be 42% silver with the correct number of 6. That is a really good question. All right, let's go to number 8. It says a large piece of silver metal is placed in 125 milliliters of 1.50 molar potassium nitrate solution that has been acidified. Nitrogen monoxide gas is produced in the redox reaction shown. We want to calculate the volume of gas produced under a pressure of 75,000 pascals and a temperature of 10 Celsius. So again, as soon as you see a Celsius temperature there, you want to change that to Kelvin, so that's 283 Kelvin. You probably also want to change the pascals. This would be 75 kPa there. Now, again, this is a chemical reaction, so you want to write your equation. It's already actually written for you, but if you notice, it's not balanced. So let's balance it together. Look at that. This is a redox reaction, my favorite type of reactions to balance. So if you recall, to balance a redox reaction, first you split it into the 2 half reactions. So Ag produces Ag plus. The other half reaction would be NO3 minus yielding NO. Next, you balance all the atoms that are not oxygen or hydrogen. So 1 silver, 1 silver, 1 nitrogen, so that's good. Next, you balance your hydrogens and oxygens. You start with the oxygens and use water to balance them. And so for this one, no oxygens here. Here we have 3 oxygens. Here we have 1, so we need 2 more. So we're going to add plus 2 H2O. Next step is your hydrogens. You balance those with H pluses. And so here we don't have any H pluses. Here, none. Here we have 4. So we need to add 4 H pluses to this side. Next, we balance our charge using electrons. So here the charge is 0. Here the charge is positive. Remember, you add your electrons to the more positive side. So you're going to add it to here, and you would add 1 electron, so now the total is 0 on both sides. For the other half reaction, here we have plus 4 and minus 1, so this is a total of plus 3 on this side. This is neutral, so remember you add your electrons to the more positive side, and so we said this was plus 3, this is 0, so we need to add 3 electrons to the reactant side. Next step is, if necessary, you want to multiply one or both half reactions by an integer so that your electrons are equal to each other. And so here we have 1 electron, here we have 3 electrons. The electrons lost need to equal to the electrons gained, and so we need to multiply this side by 3. So you're going to get 3Ag yields 3Ag plus 3 electrons. Next, we're going to add our two half reactions together. So we're going to get 3Ag plus 3 electrons plus 4H plus NO3 minus yields 3Ag plus 3 electrons plus NO plus 2H2O. If we did it correctly, our electrons should cancel. Looks like nothing else cancels, so let's rewrite that. 3Ag plus 4H plus NO3 minus yields 3Ag plus NO plus 2H2O. Let's check that this is correct. It's our equation here. So we need to check our silver, we need to check hydrogen, nitrogen, oxygen, and the charge. So let's see, silvers, we have 3 and 3, that's good. Hydrogens, we have 4, 2 times 2 is 4, that's good. Nitrogen, we have 1 and 1, that one's good. Oxygen, we have 3 on this side, here we have 1 and 2, so that's 3. Let's look at the charge, this is neutral, plus 4, minus 1, so that's a total of plus 3. On this side, plus 3, 0 and 0, so that's a total of plus 3, so that checks, so that's good. So let's look at the question, what it's really asking again. So we want to calculate the volume of the gas produced, so that would be NO gas. So we're looking for the volume. We know that it's at 75 kPa. We know that it's at 283 Kelvin. We also know that we have 125 milliliters and it's 1.50 molar of the potassium nitrate solution. Now, I don't see potassium nitrate here, but basically there's the nitrate. What about the potassium? Yeah, the potassium is a spectator. So the potassium nitrate solution basically contributes the nitrate ion there. And potassium nitrate, for every 1 mole of potassium nitrate, you'd have 1 mole of nitrate ion. And so we can use those numbers for the nitrate here. So that's 125 milliliters, so 0.125 liters, and then 1.50 molar, or you can write 1.50 moles per liter. All right, so let's look at it again with the numbers written. So we're looking for for volume of NO. So what we can do, since this is stoic, you always find the moles of the substance you have enough information about. Then you go to the moles of the substance you're interested in, and then you answer the question. So we're going to start with moles of nitrate. Now, can we use PV equals nRT for this one? We can't, because this is not a gas, right? This is a solution. So the only way to find the moles here is to use the molarity and the volume. So let's do that here. So we have 0.125 liters of the nitrate. We're going to put liters of nitrate on the bottom, moles of nitrate on top, since we're trying to find moles. And you can link between the moles and the liters of a solution using its molarity. It's 1.50 moles per 1 liter. The other way, again, that you could do it is you can say molarity is moles over liters. You're given the liters, you're given the molarity, so you can solve for the moles. All right. So that gets us to moles of nitrate. Next, we want to find moles of the substance we're interested in, so basically moles of NO. I can use the molar ratio for that. So moles of NO3 minus moles of NO. And after all this balancing, it's a 1-to-1. So that gets us moles of NO. All right. So that is going to be equal to 0.1875 moles of NO. I was trying to find the volume of NO. I have the moles, I have the pressure, I have the temperature. So guess what? I have 3 out of the 4 variables for PV equals nRT, and I can use PV equals nRT because this is a gas. So let's do that. PV equals nRT, doo-dah, doo-dah. Let's see, pressure is 75 kPa. Volume is what we're trying to find. And we just got to be 0.1875 moles. And again, this is for NO gas. R, because our pressures in kPa, we're going to use 8.31 kPa times liters over mole Kelvin. And my temperature is 283 Kelvin. And so my volume is going to be equal to 5.88 liters. All right, next we're going to look at molar mass and gas density and their relationship with basically PV equals nRT, or the ideal gas law. Remember that I told you at the beginning of the year, we're going to learn like 10 different ways that we can find the molar mass, so this is one of them. And obviously it applies for a gas. So let's look at density, the density equation. So density is equal to mass over volume, right? And the ideal gas law is PV equals nRT, doo-dah, doo-dah. We also know that moles, N, is equal to your mass over molar mass. If I wanted to find moles of something, I would take the mass of it divided by the molar mass. So capital M there, that's molar mass. So if I were to plug this in for N into PV equals nRT, I would say PV is equal to M over capital M times RT. If I were to manipulate that so that I have M over V, so basically I move my V to this side and then everything else to the other side. So that would be Cm over V. Since volume is moving to the other side, it's going to be in the denominator. And then that's going to be equal to P. And then you're going to move everything else on the other side with the P. So the molar mass would go to the numerator. R and T would go to the denominator. And so M over V is equal to P times capital M over RT. M over V is basically your density. So I can substitute D for M over V. So if I do that, D is going to be P times the molar mass over RT. So I can use the ideal gas law to really solve for density of a gas. Or what if I wanted to solve for the molar mass? Well, I can do that too. So let's look again at PV equals nRT. Again, I'm going to substitute mass over molar mass for N. So this part right here for N. And so now if I solve for the molar mass for this right here, then I would move it here and I'd move PV over to the other side. So if I solve for molar mass, that's going to be equal to m times RT over PV. You can write it this way, that is acceptable. Or you can say that m over v is density. So you can say that m is equal to density times RT over P. I'll have to check, but I think one of these two equations is on your green sheet. I don't think both of them, but I think one of them is on there. But if not, you should be able to derive it by plugging in this into PV equals nRT, basically. So let's try a problem. We want to calculate the density of air at 22.0 Celsius. Let's go ahead and convert that to Kelvin before we forget. So 22 Celsius would be 295 Kelvin. And 745 millimeters of mercury, so we're given temperature and pressure. If the atmosphere is composed of 80% nitrogen gas and 20% oxygen gas. The remainder of the atmosphere is composed of traces of CO2, SO2, H2, He, and Ar. So, since I want the density, I can use the equation that I just got above, which is D is equal to MP over RT. So I'm given the pressure, I know R because it's the ideal gas law. I'm given temperature. Molar mass is the tricky one here. So I know the molar masses of all of these substances. But I want the molar mass of air, which is a mixture of all of these. So it's telling me that it's 80% nitrogen, 20% oxygen, the rest is negligible. So what I can do is I can say, well, the molar mass is going to be 0.8 times the molar mass of nitrogen, which is 28 grams per mole, plus 0.2, which is 20%, times the molar mass of oxygen, which would be 32 grams per mole. And so the molar mass of my mixture of air is 28.8 grams per mole. And now I can plug in my values. So D is equal to 28.8 grams per mole. P is 745 millimeters of mercury. R, since I'm using pressure in millimeters of mercury, I'm going to use 62.4 millimeters of mercury times liters over mole Kelvin. And T is given to me as 295 Kelvin, and you solve for the density. Let's look at the units that we're going to get. So moles cancel with moles. Millimeters of mercury cancel with millimeters of mercury. Kelvin here cancels with Kelvin, so it looks like I'm going to get grams over liters. And my answer is going to be 1.17 grams per liter. Alright, let's do one last problem. So we have 0.100 grams sample of a compound with an empirical formula CH2F2. It occupies 0.0470 liters at 25 Celsius. Let's change that to Kelvin, so that's 298 Kelvin. 755 millimeters of mercury. We want the molecular formula of the gas. So we have the empirical formula. We want to find the molecular formula. Remember that the molecular formula is a multiple of the empirical formula. So we've always, in order to figure out the molecular formula, we would take the molecular weight divided by the empirical weight, see how many multiples that is, and then we can know how many multiples the molecular formula is compared to the empirical. So for the empirical weight, I can just basically add up my molar masses for these to figure out the molar mass, or the empirical mass, basically, of that compound. So let's do that first. So the empirical weight is going to be equal to carbon is 12.0 grams per mole plus 2 times hydrogen is 1.0 grams per mole plus 2 times fluorine, which is 19.0 grams per mole. And so if you add those up, my empirical weight is 52 grams per mole. So that's the empirical weight. Now we need to find the molecular weight. So since this is a gas, I can use my manipulation of the ideal gas law, the one to solve for the molar mass or the molar weight. Molar mass is mass times RT over PV. So then that's equal to, it's a 0.100 gram sample times R. Now since my pressure here is millimeters of mercury, I'm going to use 62.4 millimeters of mercury times liters over mole Kelvin. Temperature is 298 Kelvin divided by my pressure 755 millimeters of mercury, and my V is 0.0470 liters. If you calculate that, let's check our units here. See, liters will cancel with liters, Kelvin cancels with kelvins, millimeters of mercury cancels with millimeters of mercury. You end up with grams per mole, which makes sense since it's molar mass. And you get 52.4 grams per mole. So now back to our comparison between the molecular weight and the empirical weight. We got the molecular weight to be 52.4 grams per mole. The empirical weight was 52 grams per mole, so it looks like that's a 1. So basically the molecular weight is the same as the empirical weight, which means the molecular formula is the same as the empirical formula, so it's CH2F2. Alright, that's it for the notes. Hope you guys have a great day.